we are going to be talking today about line of sight radios, specifically in our wireless session. This is number one. We're going to do this again for week 2 next week with the concept of will it work? And we came up with this just because we asked a number of our customers over the years and a number of system integrators, what's the number one thing with wireless that is your biggest challenge? And they all came back and said, will it work? We're made lots of promises, and we don't really know if this will fundamentally work. It seems like sometimes it does, sometimes it doesn't. So we wanted to give you 20 years of experience that we have dealt with all these various issues, and we're just going to go through some of just the line of sight today, and then we'll deal with some of the other items next week as well. So here's some of our objectives for today that we are going to try to go through. We're going to get the basics down of line of sight radios, and we're going to try to give you some gotchas, some of those things that over the years that we've just run into and said, oh, you know what, this really tripped us up, or this tripped up customers that we went and talked to. So we want to make sure that we help you understand some of those. So let's go ahead and kick us off here. All right. So here's a great slide that I came across about 6 months ago or so, and this was in the midst of a presentation that someone was doing, and they were talking about when a plant is taking a look at a new application, specifically what wireless applications are available to them today. And this isn't even all of them. This is probably only about half, I would say. There's plenty more that I recognize that aren't on here, but this particular one just shows a little bit about how overwhelming it is when someone is trying to make a decision on what wireless to use and how it works and all this sort of things. And so that's part of session number 1 today and session number 2 next week that we want to deal with. So if we look at this, there's an X and Y axis on this, and the X axis specifically talks about distance, and it's distance in kilometers. So everywhere from 0.01 kilometers to about 100. So you're looking at many, many miles, probably 50, 60 miles on the high end, and very, very short distances on the low end. And then on the y-axis, we have data throughput, and that's put in terms of megabytes to gigabytes per second. So on the top end, it's 1 million kilobytes per second. So we're looking in the gigabyte stage. And then on the low end, very, very limited with what it can see. So what this tells you is if we look at some of these different protocols that are apparent on here, we'll see that some of them are really good for short distances and can give you some pretty high throughput rate. Others are good for long distances, but maybe don't give you much data that you can put through those. And some of them are decent for all of the above. And so how do they get there? And so you might recognize one that's been in the news a lot lately, 5G. We're going to talk more about 5G next week, not this week. This week, we're going to talk more about just the line of sight radios, which are traditionally the ones that are down in here. They can send some short types of data, but longer distances. So we're going to talk a little bit about that today. All right, so let's talk about some of the wireless spectrums that you're going to deal with overall. Specifically, we have 3 that are our main ones that we deal with on the line of sight side of things. So if you go back probably 20, 30 years, the 400 megahertz range was specifically what we saw that a lot of people would use, and it was a licensed radio. So the FCC had to grant a license for you to use something in this range, and they would give you a specific frequency somewhere between 400 and 470 usually. And they'd let you put about 10 watts of total power out there as you sent a digit of some sort, an on-off, or a simple measurement of maybe a flow meter or something that might be remote. So it was very slow speed. You're not sending a lot of data through it, but it was strong power and distance. You could get 20, 30 miles line of sight fairly easily with a licensed radio that was going 400 megahertz. Then, if you look back into the 90s, the FCC opened up a new frequency range that was that 900 to 900, roughly 28 megahertz range, and that suddenly gave you a little bit more speed. You could do a lot more with this. You could send a lot more, and it was now unlicensed. We didn't need the FCC. As long as we didn't exceed the total power that they allowed, which is 1 watt, we could then be unlicensed. So that meant that anyone could put these 900 megahertz radios in their plant, and a lot of people started to do that. It gave them still decent power, not the same power as a licensed radio or the slower megahertz range of 400, but it was still fairly strong power and distance. So I'd say 5 miles line of sight was not uncommon for people to be able to do. And it was a faster speed than you got with that 400 megahertz range. And then as people needed more and more, they wanted to do more. They wanted to put Ethernet and those sort of protocols and Wi-Fi and that sort of thing. We had to bump up to a bit of a faster range. People tried those over 900 megahertz and it was okay, but not awesome. So they bumped up to that 2.4 gigahertz range, still unlicensed, but now it started to get us much, much faster speeds, but it really limited the distance that we could go. So you could imagine in your home, you're using 2.4 gigahertz, most likely for your Wi-Fi router and modem that you use there. You probably have it for some phones in your house. 2.4 gigahertz is used in a lot of places now, fairly common. So these are the different frequencies that you saw industrial plants using to get line of sight radios and what they would specifically send. 900 megahertz is kind of that middle ground. And so we picked that one just to talk a little bit about some of the things that we recommend that you do in order to deploy this. So number one, and whether you use any of those three protocols, we really, really strongly recommend that you do a site survey. A site survey is something basically where either you or someone who's familiar with deploying this, maybe a system integrator of some sort, would come out and they're going to explore what other frequencies exist. They're going to do that through just doing some things that sense the other frequencies that might be present. They're going to look for different antennas that might be present on roofs and other places that would tell them there might be another system already going. They might have to talk to your IT team to find out if there's something else that they should be aware of. But one of the things that they're really going to look at, besides other people using the frequencies that you want to use, is they're going to look for a signal to noise ratio. So they're going to look for about a 15 dB difference that they're going to find ideally in order to be able to send that signal pretty consistently. So we're looking for a noise level where noise often is anywhere from about negative 90 dB to I'd say negative 120 dB is pretty common for noise in the background. That's just frequency noise that exists for a variety of reasons. But if they see something else in there that is sending a signal purposely, they might start to see signals that are much higher. And now that's going to cause more and more of a problem for you to send it. So we really want to see at least 15 dB difference between the noise in the background and our signal that we're trying to send. So we want to maximize the signal that we send, but not so much that we do things that are bad for our neighbors. We don't want to blast our neighbors, just like someone who's throwing a party and is blasting that radio. We don't want to blast our industrial radios either. Not that you'll be able to hear it, but it would interfere with other signals that other people are trying to do. So specifically the 900 megahertz, that middle range that we talked about, it's slower than 2.4, but it's much stronger. But it's faster than 400, but it's not as strong as that. So one thing that you really have to be careful of, this is one of the gotchas, is if you're doing any of these, you can't exceed the total power. So 1 wattage of power is really our limit that we're allowed to, and for 900 megahertz and 2.4. So what we're looking at is the output of the radio. The radio has some sort of a gain that's sometimes adjustable, but often it's a fixed amount that radio has. It might be, let's say, 100 milliwatts that might have, would be an example. And then you have loss on the cable. The cable is always a loss, so it's a negative. It's going to take away from the total power that you have. And the longer that cable is, the more it's going to take away from the total power. And then you have an antenna gain. So that antenna is going to take and put a certain amount of gain on the whole thing. And so this whole calculation has to be no more than total 1 watt of power. In an ideal world, we like to see most of our power here, not as much as our power here, because that antenna is going to imply a gain that's going to then get put all of the stuff that comes from the cable and all the stuff that comes from the antenna, any other things that it's picking up, that antenna might be spreading some of that as well. So we really want most of our gain here if we can, and not have to have a massive antenna that can be amplifying noise for people and for the signal itself. One thing that we wanted to make clear too is that with 2.4 gigahertz and like the 5 gigahertz range, those can handle multiple protocols. We're going to talk about protocols a little bit later, but we want to make sure that we recognize that the 400 and the 900 range, they can only handle one protocol, and really often can only handle just one type of signal, on-offs, 4 to 20s, that sort of thing. One other gotcha we'd warn you about is that many of the radios use a send on exception. And so if the send on exception might be to preserve battery or to minimize noise and frequencies getting sent out there, you could have a situation where that antenna suddenly stops working because maybe it got hit by a tree, or you had a lightning strike or something. And now, because the thing receiving it on the other end, that radio is waiting, doesn't see anything, it assumes everything's fine. The reality is you might have a problem. So we can say, as a gotcha, make sure you consider maybe using a heartbeat signal so that it occasionally sends something out just to say, I'm alive, I'm functioning. Next up, we want to talk about antenna placement. Antenna placement is pretty important, and there's a lot of gotchas here that you can run into, certainly. So if we look at this on the left-hand side here with the red antenna and the blue antenna, this is going to be our transmit antenna, and this is going to be our receive antenna. So we have to get from point A to point B. And what are some of the things that we look at that are important? And we run into this all the time where people will ask us to come in and say, hey, we bought this system and it never worked. And typically we find that the problem was related to antenna placement. We want you to remember 3 different things with antenna placement that's important. Number 1, the height. Number 2, the direction. And number 3, the type of antenna. So the height is pretty important because we call these line of sight radios. And in an ideal world, they do want to see the other antenna that they're shooting to. So if you have a large curvature of the earth because you're trying to shoot this 5 miles, you might have to get both antennas up high enough to make sure that they can see each other. And that might be a height issue that you have to deal with. Number 2, we talk about direction. So there's a few different types of antennas. We're going to name 2 of those today, the 2 common ones. And one of them is more of a directional antenna. And so certainly, if you can't see the other antenna that you're trying to aim at, and one of them is a directional antenna, it's very possible that you could aim it this direction and completely miss that other antenna altogether, or the signal might be so weak that you don't have a very consistent signal overall. So direction is really critical and important here. Last of all, the type of antenna. So we're going to talk about that in a second, the different types. But we wanted to show you there are some things that are important to be aware of. Number 1, you can bounce the signals off of objects. So for instance, if you're a water plant, you could bounce it off of a water tank. That's certainly possible. You could bounce it off any metallic tank if you're maybe a tank farm. You will be able to bounce the signals in between that. Number 2, you can go through obstructions. Not usually metal ones, but you can go through certainly concrete, trees, that sort of thing. But everything it goes through weakens it. There's an absorption that occurs on those obstructions. So just something to be aware of. Last of all, there is a diffraction. You can go around objects, and we're going to teach you a little bit about that, but it's not ideal. Ideally, we don't want to have to kind of bend it around things if we can help it. So here's our 2 types of antenna that we're going to talk a little bit about. We're going to talk about a Yagi and a collinear antenna. Yagi was named after a guy in the 1920s from Japan that developed this specific type of antenna. And in this particular type of antenna, it uses as you can see, a long line here with a bunch of nodes. And the more nodes that you have, the more power and direction, the more pointed the direction becomes with this. So if you have a short one that only has 2, it usually doesn't have as much strength, and its beam isn't going to be quite as directional. It'll be a little bit more wide, which we'll show you in a second. The next one's called an omni, or a collinear. And for many of you, you probably in your house have a 2.4 gigahertz wireless modem, and it probably has one little tiny one of these. We call it a whip antenna, but it's effectively a collinear or an omni antenna. So these are our 2 basic types. We normally recommend this for directional, the remote site, and this for the base station where you're trying to shoot to. Here's how they work. So a Yagi antenna, if you look on this piece over here, the Yagi antenna, if we superimpose this onto this, we would see on the back end, it kind of looks like a goldfish, but on the back end, it's got a few little nodes that are kind of shooting out the back. So there is some back end signal that does get sent out, but that signal is not ideal. If you look here, you can kind of see what's going on. Here we have what's called in-phase signal that's going out the front of this, going out this direction. And that's healthy signal that's going to go where we want it to go. The back end of it is out of phase, not going to be as good, not going to get you as strong a signal. So we really try to make this just for directional. But you can see here, it's not just one solid line. It's kind of an orbital thing here, or almost a rugby shape to a certain extent, a rugby ball shape. And so there is a shape to this, and we call this the Fresnel zone. We'll talk about that in a second. This is a collinear, an omni. This is what it looks like. So over here, you can see, while there's nothing on the up and down, if we superimpose this over here, there's nothing on the up and down. There's nothing straight up, there's nothing straight down, but in all directions, 360-degree directions, we've got a significant amount. You can see it here, you see it shown. We've got a significant amount of signal going out in all directions, but nothing straight up and nothing straight down. So let's imagine that we've got, we're sending it from building A to building B. And in this particular case, we have a directional antenna that we want to shoot over here. And here we might have that collinear or omni that we want to receive it. And here's that Fresnel zone, that rugby ball shape that we talked about. And it's actually, you can calculate how it's going to work. So we can help you if you ever need help with that. But one of the things we want you to be aware of, while we can use this to bend around things, so like if we had something that was here, we could bend around it, but we have significantly minimized the power of this signal by doing that. We ideally want this to be entirely unimpeded to maximize all of the power, have nothing in phase, out of phase, as you saw in that earlier picture. We want this to totally be able to send that full signal over. So that means we want to have it far enough off of the buildings, far enough away from walls, far enough away from trees or other things that might interfere with that, if we can help it. If we can't, we just shoot through those things, but we might have to boost the power a little bit to get through to the other side consistently. So just a quick reminder on some of these things. We want to show here that one of the big things that we see is that the alignments are done accurately, our signal quality would be good, our reliability would be good. One thing we don't like to see is when people don't bother to do this well, and instead they just put the biggest antenna they can and just blast everything to try to get through. That creates a lot of noise and a lot of problems for other neighbors or even people within your plant that might want to try to use it. So here's some wireless best practices for the antenna and that sort of thing that we have learned over the years. We just wanted to give you some warning about. So number one, weatherize your panel, weatherize your conduits, even consider sealing your conduits, and all the connectors that you make as well, from the antenna to the cable to the panel. Weatherize those things. This is one of the number one things that we see that will take down a well-installed system over 6 months to a year. Is slowly water works its way in. Water works its way into the conduit, water works its way into the panel, makes its way into the connectors. This is the number one thing that we see is water ingress takes down good installation. So make sure you weatherize and seal all of those things as well as you can. Number two, use surge and lightning protectors. This is a big one. And make sure you ground them. We just went out to a site about a month ago, and they had a lightning protector in place, and lightning hit, and it did nothing because it wasn't grounded. So the lightning took out the whole of the panel, unfortunately. We also would remind you, though, too, ideally you do surge and lightning protection not just on the antenna cable, but also on the power mains and all inputs, outputs, and comms cables going in and out of that panel. So ideally you protect all of them and make sure they're all well grounded. And last of all, another big one is don't put that antenna too close to another antenna or too close to another building. Really need to take into account that overall Fresnel effect and how it might impact by being too close to a building or too close to another antenna. Let's go ahead and finish this off here. So wireless Ethernet came into being on the industrial sector, first at the 900 megahertz and then with the 2.4 gigahertz. So I won't spend too much time in the 900 megahertz one, only to say it works a little bit differently than the regular 900 megahertz where we're not doing Ethernet. Specifically, what will happen with the 900 megahertz is they'll break things into bands. We have specific bands, and if you're familiar with setting up your modem at home, you'll recognize this. So 2.4 gigahertz, those bands become channels, and so we call them channels, 1, 2, 3, 4, 5, 6. And so when you set up your modem at home, it's probably set up typically for like channel 1, 2, and 3. And so you can see each one of those is 22 megahertz wide at that 2.4 gigahertz range. And so if you have it set up for number 3, and you also have your neighbor next door set up for number 3, and your neighbor to the other side set up for number 3. You're all blasting right here. If you just make the simple step of changing to like number 11 or something up here, now you'll be sending your signal with much less interference with what they're doing. Even though they're still in the 2.4 gigahertz range, you'll be having very little interference because you guys aren't together. So this is just one important gotcha we also see whenever you're setting up an industrial wireless for 900 megahertz or 2.4 gigahertz. Make sure you check the channels, and a site survey would be something that would check that. All right, we're going to finish off here with Ethernet protocols for the high frequency radios. These are things that for line of sight radios we have seen really come into play a lot in the last 10 to 15 years. So Modbus TCP is one of the common protocols that people will use on the Ethernet radios, and this is a very common protocol that's been around since the 80s, but TCP specifically uses the Ethernet packets. This is very, very common. The one catch with it is that it uses a master-slave, and the master-slave, if something happens, the slave doesn't necessarily always know to tell the master what's going on, and so this particular one does have some weakness there. One of the flip side of that is Ethernet IP. So Ethernet IP, people really like this. It's a growing one. It's a PLC favorite nowadays for certain PLC manufacturers. So Ethernet IP is becoming very, very common. It's a little bit faster, typically, than Modbus TCP IP. It's a little bit easier as far as overall configuration, but it's not as strong from a deterministic standpoint, meaning from a time-based standpoint. So if you're trying to do control and safety and some other things, Ethernet IP, you really have to do a super job with your overall network design to make sure that you don't have time interferences. DNP3 is a common one. This has been around for a long, long time, but it's really getting a lot of acclaim for people that have to meet regulatory. So like the power industry, the water, wastewater industry, where they have a SCADA system that's talking to an RTU. DNP3 is becoming very popular, especially because of this timestamp, where all the protocol and the packets on that protocol have a timestamp that says when it's sent. So from a regulatory standpoint, if you lose your signal for a period of time, now it's going to come back and kind of restore everything, and all the timestamps are still there, so you know when things happened. That's why that's becoming quite popular. Last of all is wireless HART. And wireless HART is one that's pretty common. We're going to talk about that and show a picture of it to show why it's getting pretty popular. So here's Modbus TCP. We mentioned that one. And it's more of a master-slave, so you have your HMI or your SCADA system up here, and it's constantly sending a signal out there to grab what's going on down on this end. DNP3, here's a picture of that where we have our SCADA system, we have some RTUs, and we might have that signal be sent over, you know, in the old days they used it over twisted pair or a dial-up lease line. Now it's more done through radios and that sort of thing, but people really like it. Even though it's not as fast, they like it for that timestamp. But wireless HART, there's about 30 million HART protocol devices out there, 30 million plus. And wireless HART gives people the ability to grab that HART signal now and tell more than just the process variable. So wireless HART is becoming quite popular for that reason. And it's become, I'd say in the last 5 years, more and more deterministic. This is one of the things that they're trying to do, so it gets more time-based. They're trying to design that in as the newer wireless HART protocol is getting released. So this is a really strong thing that is becoming popular. And here's one of the other reasons why. It's because it can be meshed. And so wireless HART is designed to be meshed. And what does that mean? Well, rather than signal A going to signal B, and that's the only path, now all these devices have multiple ways that they can travel back and forth, and they can talk to each other and set up multiple paths. So if you lost this path because a giant tree fell over and blocked the path, or a truck drove in front of you and now the signal can't get from point A to point B, it's going to go out and seek other paths. That's called meshing. And that's where wireless HART is really becoming quite popular because of that meshing capability. All right, so let's finish off. Some of our do's and don'ts, and just a reminder overall of good practice when it comes to designing a wireless system overall. Okay, so number one, we have a really good understanding of what data is being sent. That's really, really important that you talk with your system integrator or your control engineer, whoever's designing your system. We want to have a good understanding of what data is being sent, who needs to see that data, and what were to happen if it didn't go through. Like from a regulatory standpoint, if you lost 5 to 10 minutes for whatever reason, what happens? Who gets mad at you? How do you have to deal with that? So this is a really important thing you need to discuss with that integrator or control engineer. Next up, think through all the environmental impacts that might exist throughout an entire year. So what about the leaves on the trees? What about other industrial noise and traffic and that sort of thing? So think through all the environmental impacts that might exist. If you're doing a site survey in wintertime, as an example, there's no leaves on the trees, that's a problem. So you need to take that into account. What other signals might be present that maybe turn on and off occasionally? That's why it's important to talk to your IT people or other, even your neighboring industrial folks that, hey, do you have an industrial wireless system running that I need to be aware of? That site survey, so critical. Site survey will help to tell you all kind of important things that you need to know about. So that site survey, I can't tell you enough to do that. Weatherizing your panels, we talked about that. Just making sure that you weatherize all the connections, weatherize all the conduits. Over and over again, I hear about people, the system works until water gets in there and causes problems. Lightning protection, we said that was so important, and don't forget to ground it. So many people forget that piece. And putting lightning protection on all of the different pieces. If you put lightning protection just on your antenna cable and forget to put it on your panel power, or forget to put it on the I/O or the comms, you still have a place where if lightning hits nearby that it can get into that panel and take things down, often at the most critical point when you need it. One of the big things that's becoming popular now is battery life, and more people are trying to do this off of battery, maybe even with solar. And so you need to really think through all those issues and understand, how long do I want the battery to last? If that vendor is promising me that this battery is going to last 5 years, is that reality? Is it really going to last 5 years based upon me sending data every 10 seconds as opposed to every 30 minutes that they were calculating this around? So think through all that, really talk that through with your integrator or control engineer, whoever's designing it. Make sure you really have an understanding of how long that's really going to last. And last of all the protocols. I can't tell you how many times we run into situations where we have protocols, even sometimes the same protocol from different manufacturers, and they just don't talk well. So make sure that this is thought through beforehand, because this is another one that can really take you down.